who is our speaker. It's a pleasure to have him here in our institute today. He is a very well-known expert on studies of blazars and relativistic jets in AGS, especially with ultra high resolution VLBI studies, and lately he has started to move in the spectrum to study the connection with very high energy emission, and also the connection with ultra high energy particles detected by the current particle detectors. He made his PhD in 2000 in Moscow in the Lebedev Physical Institute, and later he had two consecutive fellowships. One of them was the Jansky Fellowship at the National Astronomy Observatory of the USA, and later he moved to the Max Planck Institute for Astronomy in Bonn with Alexander von Humboldt fellow. Since 2019, he moved back to Russia, where he was the project scientist of the Radio Astronomy space mission that was absolutely successful. Perhaps you have heard about the results. And then he moved back to Germany, to the Max Planck Astronomy Observatory, Max Planck Astronomy Institute in 2022. He's where he's right now, actually leading a research group funded by an advanced ERC grant for the study of multi-messenger AGN studies, which is the topic that he's going to touch in this talk. So, Yuri, thank you very much for being here, and yeah, the floor is yours.
Thank you. You have a proper pointer. May I use it, or it's only for locals?
It's actually my favorite. This is the one that I use for my PhD presentation. Actually,
Sold
20 years ago.
Okay. Thank you for the nice introduction, Ivan. I would like to make one more comment before I start. That I at least like to be interrupted during the talk because then I get some message that people are listening to me, and also I see what is interesting for you. So if you see something which you want to discuss, please don't hesitate to interrupt me, to ask questions or give comments. And now to the talk. So I will discuss today high energy blazars at parsec scales, and why do we care? What is interesting? What are open questions today so exciting that we spend our time and also European money on trying to answer them? So active galaxies are known to be particle accelerators for many decades. At the same time, theorists for many years were telling to us that they understand how these machines can accelerate electrons to very high energies, right? To relativistic energies. Talking about massive particles like protons, we mostly heard the claim that it is impossible or very complicated. At the same time, observationally, since relatively recently, we have several indications that actually active galaxies can be efficient accelerators even for massive particles, right? So what do we know about active galaxies? Supermassive black holes with accretion disks which energize or which feed center supermassive black holes by matter. About 1/10 of it is accelerated away in the form of relativistic jets. And radioastron was already mentioned by Ivan. Radioastron has found out that actually cores of active galaxies are extremely bright, again, much brighter than the theory predicts. And this is an indication, a strong indication, if not of proton acceleration, even though extreme scenarios have suggested that, but at least of very efficient mechanisms of particle acceleration or reacceleration. On top of that, or in parallel to this result, we have this wonderful ice cube, like first, I would say probably second big news that a high energy neutrino was associated with the blazar, and neutrinos are very strong indicators of proton accelerators. I will discuss in the next slide why. So we have a number of indications that active galaxies know how to accelerate protons to relativistic energies, and we want to learn from them. That's basically the idea of our study. Now a few words about the neutrino astronomy. I have learned all of that myself, and I still know very little about this. So I learned about it over the last several years, and moreover, me and my group came to the wonderful Granada this week exactly because we want to learn more. So in the Granada University this week came FRENET, the European Neutrino Telescope and European Neutrino Collaboration is organizing a boot camp, and they will train us how to actually operate and calibrate and analyze and simulate the data coming from a European neutrino facility. And here I would like to say a few words on how you do it on the basis of an example coming from IceCube, from an American telescope which is located in the southern hemisphere, in the South Pole, and they use ice to detect neutrinos. So the way how it works, neutrino come from space, and they interact with the matter, with molecule of water with a probability of 10 to the power of -5, -6. And then a muon is produced, and the muon is a charged particle. So a neutrino is not charged, muon is a charged particle. And when a charged particle moves through a matter with a speed faster than the speed of light in this method, then you produce Cherenkov radiation. And then there are 5,000 optical models, optical sensors around, in this particular case in ice, covering a cubic kilometer. And basically you measure the trajectory of a muon from the Cherenkov light. You detect the Cherenkov light by the photon multiplying tubes, and then you reconstruct the trajectory. And from the trajectory, you get the following parameters of a muon, and then you kind of extrapolate it to neutrino. You get of course, the moment of time when it arrives. You get the energy from the trajectory, very complicated, not very accurate, and also you get the position from the sky. And the typical positioning, so the accuracy is around 1 degree. They work towards improving this accuracy, but it's not only random errors, but also systematic errors are significant, probably even dominating the overall error budget when you reconstruct the position on the sky. And the reason why we care about position of the sky is that neutrinos is not a cosmic ray. So cosmic ray particles, they are charged, neutrinos are not charged, so their propagation in the universe is not affected by the magnetic field. So that is why they directly point for us the position on the sky where they were produced. So they directly point the position on the sky where a proton accelerator is located. At the same time, if you take a look at the histogram, at the plot, and since it is translated over Zoom, I will sometimes use the pointer on my screen so that people on Zoom can also see it. So this is a histogram, the energy of a muon detected, and this is a number of events detected by IceCube over several years. And you can see that the total number of events in black is dominated by a noise. And by noise, I mean muons which are produced in our atmosphere due to an interaction of cosmic ray particles with the atmosphere. Okay, so it is completely and strongly, because this is a logarithmic axis, dominated by a background. And the astrophysical signal is several orders of magnitude lower than the background at the energies like the main energy of IceCube Neutrino Observatory, around 10 to 20 MeV. But then going to very high energies, like more than 100 TeV, around or more than 100 TeV, then your signal starts to be dominated by astrophysical neutrinos. So everything what is generated outside of our atmosphere, and that is why we prefer to work with neutrino events which are very high energy, because the probability for them to be of astrophysical origin is very high, is around or higher than 50%. Now, what are the sources of high energy neutrinos? Even though I'm giving this talk about active galaxies, and I will argue within my talk that active galaxies do know how to accelerate protons and then produce neutrinos, this is completely not finalized, put in stone, fixed in stone, solved problem. No, please don't get me wrong. As of today, active galaxies are thought to produce up to 10%, are estimated to produce up to 10% of the overall astrophysical neutrino signal. Tomorrow, this number might change to less than 2% or less than 50%. Statistics improves and our analysis improves, but as of today, we believe that up to 10% of neutrinos come from active galaxies, up to 10% come from our own galaxy, another is from ice cube, but everything else, we don't know from where. It can be fast radio bursts, it can be tidal disruption events, you name it. And that is kind of why I wanted to spend these several very important minutes discussing this slide. I wanted to share with you this feeling, this thought, this message that this is a very new and exciting field. And it is a field where there are still many more questions than answers. Because of that, it is exciting to do. It is also quite painful because people are very eager to get results first and not always very friendly with you. But it is at least fun. It is fun, okay? It's not boring at all. So we still don't know. Now, coming specifically to active galaxies, but before doing it, I would like to ask you to take a look at this plot, and this shows to you how you can produce neutrinos. So it is either from, most probably, I mean, there are many ways, but most probably they are produced by an interaction of either proton-proton or proton plus high energy photon. They're called PP or P gamma. I will use this notation in my talk. So and you always require relativistic proton. That is why neutrinos are so interesting, because detecting neutrinos from deep space guarantees that protons are accelerated in space. Of course, we knew about it from cosmic rays, but cosmic rays are not very helpful in pinpointing the place where protons are accelerated. Neutrinos are the ones which tell you exactly where protons were accelerated. And so then you produce, from pion decay, you produce neutrinos, and they are accompanied by gamma ray photons. However, you will see them or you will not see them will depend on opacity properties of the region where neutrons are produced. So in the early days of neutrino astronomy, of high energy neutrino astronomy, people were always looking under a street light, and the street light was emitting gamma ray photons, because everybody was expecting that you will see a gamma ray flare, high energy gamma ray flare, accompanying neutrino production. In reality, it is by far not the case, and right now there is even a proof for that coming from a Seyfert galaxy, NGC 1068, which is the highest, the most highly significant detection from an integrated neutrino signal. So after 12 years of integrating neutrino sky, IceCube has found that their highest peak comes from the Seyfert galaxy. However, the gamma ray level of emission of this galaxy is several times less than what is predicted from neutrino production. And the argument there is that it is just gamma ray opaque. So gamma ray light, gamma rays are not as efficient as originally thought to correlate, to pinpoint the source of neutrino emission. Now, I would like to switch to potential physical mechanisms behind neutrino production. And here I split them into two options. Option number one is that this production is not related to beaming. So then it is not produced in the jet, and the most probable cause today or place where protons are accelerated is corona, AGN corona, with magnetic reconnection as a mechanism accelerating protons to relativistic energies. And another option, and so NGC 1068, this Cepheid galaxy is exactly as of today, the best example for this mechanism. And then there are options for mechanisms related to the beam jet. It's either protons produced close to the jet base by supermassive black holes, I mean not produced but accelerated. Protons can be accelerated in shocks in relativistic jets, or in a surface between the spine and sheath. So you need a surface between fast-moving and slowly moving plasma. And in the surface, you can accelerate protons to relativistic energies. All of that will work fine, of course, within certain assumptions. And but this will require associated electromagnetic emission and also neutrino emission to be Doppler boosted. So we should expect Doppler boosting from this emission. And in this talk, I will discuss tests related to these physical mechanisms. Okay, now coming to a program which we are organizing to study active galaxies as potential proton accelerators and neutrino emitters. So we observe AGN jets at parsecs and subparsec scales using VLBI. So from parsec scales, we can probe jet formation, plasma acceleration, almost directly probe them from our measurements, which we perform at parsecs and subparsec scales. We can reconstruct physical properties and use parsec scale information together with multi-band electromagnetic observations, neutrino observations. We can perform multi-band and multi-messenger SED modeling. And talking about VLBI observations, we use a twofold approach. So one, we perform a continuous monitoring of a complete sample. It is the most expensive in terms of observing time and also human power than reducing and analyzing the data. However, in this way, we are guaranteed not to miss anything, because we will observe jets before, during, after neutrino events. We can come back to the data later when neutrino telescopes publish their data and not miss anything. However, we also utilize an approach of triggering on neutrino events with VLBI. In that regard, it is, of course, observing time effective, but we don't know what was happening in the source before neutrino has arrived. Here, I would like to show to you just an example of what we have done several years ago using our VLBI observation. So the program is called Mojave, Monitoring of Jets with VLBI Experiments. It has started in 1994 and is going on for about 30 years already. So from cross-correlating the measurements which we perform at parsec scales on the plot here on the screen, here is time. And in black, the Fermi photon flux, and in blue, the radio flux density coming from parsec scale core. And typically, as you can see from this histogram, we have correlated the parsec scale radio emission with Fermi gamma ray emission. We have found out that the zone where gamma rays are produced is located, so the correlation is high, and the zone is located about half of a parsec upstream, or several parsecs upstream, deprojected from the 15 GHz core. So most probably this delay and this difference in the regions from which we see electromagnetic emission is related to synchrotron opacity. And due to this opacity, the very beginning of the jet is not accessible to us. Moving from multi-band electromagnetic example to multi-messenger example, here I show to you the first case for which a high energy neutrino was discovered coming from a blazar. So this is Taxis 0506 plus 056. And as you see, in 2017, a neutrino has arrived, and it was accompanied, in this case, by a strong gamma ray flare, also TeV flare, and a radio flare has started. So actually, we do not still understand, I should say, why the delay with radio is so high. And this is an open question. But in general, this is a very strong tool to allow us to locate through multi-band and multi-messenger correlation analysis to locate the region where protons are accelerated and neutrino produced. Moving to statistical analysis of VLBI data, I would like, by this plot, to tell you the following. So first of all, this is what we measure. On the right-hand side, the histogram of observed apparent kinematics of VLBI jets. And this is the apparent, not real, but apparent plasma speed, which we see ranging from 0 to about 40 c, speed of light. And from that, we can extract intrinsic properties of jets in the brightest active galaxies on the sky, which we observe. And as you can see from the histogram, performing population analysis, we can well reconstruct how the sample properties, how the viewing angle, Lorentz factor, and Doppler factor differentiate, or their typical values for the brightest AGN on the sky. And what I would like to underline here is the following, that we limit the Lorentz factor by 50. So the maximum Lorentz factor, which we deduce from our analysis, is 50. And the maximum Doppler factor can go up to about 100. So this is important, that in case if your high energy simulations, if your high energy model requires significantly more extreme, more relativistic jets, it is not confirmed observationally. So anything on the level of 100 Doppler factor or several hundred Doppler factors is extremely rare. Or something is completely wrong with our parsec scale VLBI observations, which is also possible. But if we are doing our job well, then these are very strong limits on models for jets in active galaxies. For example, and I will talk about this later, the typical viewing angle for complete flux density selected samples of active galaxies would be several degrees, and this is the outcome of a strong beaming effect on selecting our samples. Now I move from this, and I hope you trust me that we can reconstruct relativistic parameters of jets well using direct measurements at parsec scales. I move to a multi-messenger analysis comparing the blazar properties with neutrino properties on the sky. And on this screen, in orange, you see the error ellipses of high energy neutrinos as detected by IceCube over the last about 10 years. And we ask a simple question: is there anything special? Are blazars, which are spatially associated with neutrinos, different from the rest of VLBI selected complete samples of blazars? And in Mojave, we observe several hundred brightest blazars on the sky. We reconstruct their relativistic properties. From the neutrino angle, so here we use so-called gold sample coming from IceCube. And for them, the probability to be of an astrophysical origin coming from deep space, not being generated in our atmosphere, is about 50. So altogether, from about 93 events, which we analyze here, about 2/3 of these events will be of an astrophysical origin, and 1/3 will be noise or background. Let's call them background coming from our atmosphere. And here is the result. So these are cumulative histograms going from the left to the right. This is Doppler factor, Lorentz factor, and the viewing angle. And in black, you see a distribution for the whole sample of bright blazars. And in color, you see properties of blazars which are spatially coincident with high energy neutrinos. And you have two different colors here. Basically, these are two different ways how we have selected and analyzed these high energy events. It is not very important for my talk. I don't go into details. However, neutrino community would always ask how the neutrino events were selected. So it's basically these two different colors are for them. For you, what is important is that we do see with a significance of about 3.5 sigma, then blazars spatially coincident with high energy neutrinos are typically show higher Doppler factor, higher Lorentz factor, and smaller viewing angle. So from that we conclude that neutrino production, as I have written here, should happen at subparsec scales where they just have already undergone substantial acceleration, or we would not see these special properties of neutrino blazars. They are found to be more extreme, more relativistic. We can also statistically address this by using variability information, right? Because variability information indirectly probes the same angular or the same linear scales. And in our paper about 5 years ago, we have used radio observations of these blazars, of these active galaxies, at the Ratan 600 telescope at several frequencies, and we have stacked the light curves of neutrino coincident blazars together on the moment when neutrino has arrived. So the moment when neutrino has arrived is plotted here for the delay 0. And then we have stacked all these light curves together, and we have found out that there is a peak for our highest observing frequency, which is exactly what we have expected when we have started this analysis, because the higher the frequency, the closer you probe this region of high activity, the region where you expect these high energy photons and also neutrinos to be generated close to the central engine. Because the higher the frequency, the lower the synchrotron opacity, the closer you see. In that regard, I mean, these are the frequencies available to us at that telescope. In that regard, if you can choose the frequencies, you want to go to places like Granada. You want to go to places like Iran, because the 30-meter telescope here actually gives you an opportunity to probe these regions much better. But we don't have such telescopes, or we didn't have such telescopes to our possession at the time when we were doing this first analysis. And so this was found to be the case with 2 sigma significance. This analysis was followed by a few other groups later, and you can see here for an example of an OVRA of Ansvali 15 gigahertz monitoring, and this 2 sigma significant coincidence with radio flares was confirmed. A very recent result comes even from VLAS, from the VLA All-Sky survey, which is happening right now at 2 and 4 gigahertz. And our colleagues, being excited by this question, have used the first 2 epochs from observations of VLA All-Sky survey, and they have indeed found out also a 2 sigma significant, not flares per se, because they have only 2 epochs, but variability, which is associated with high energy neutrinos. Having said that, if something interesting will happen with that, something new interesting will happen with it, it will come from much higher radio frequencies. Statistics is fine, but you want to check on your results using, going deeper into studies of individual blazars which were independently claimed to be strong neutrino associations by other groups, basically by neutrino collaborations. And here I would like to show you this story of the blazar PKS 1424. And for us, it was a very exciting story because it has indeed happened as I present to you. We said, fine, you can trust our statistical results, you might not trust them. Let's take the case, let's take the blazar which is claimed by you, our neutrino colleagues, to be one of the brightest neutrino emitters on the sky. And this on the top of this slide, you see a stacked over 9 years neutrino sky produced by ice cube. And I didn't mention this later because right now is the best time to indicate it. You remember that ice cube is located on in the South Pole, but you see here the image of the northern sky. And the reason is that our neutrino colleagues like to use the planet Earth to filter out the background, right? So basically, if you are a neutrino telescope, you observe looking underneath because the planet Earth is helping you to minimize the level of background emission. Basically, our planet will protect you almost completely from muons which are generated in our atmosphere, and all what is left in the background are neutrinos produced in the atmosphere. So here on the screen you see a combination of an astrophysical signal and a background from our atmosphere, from neutrinos in our atmosphere. And here you see Texas of 506, I have already discussed it. This is the first neutrino association by ice cube. The next one, NGC 1068, is a Seyfert galaxy, which is the highest peak on this neutrino map, and most probably, so there are no flares, it is just steady neutrino emitter. It always produces a relatively high number of neutrinos, which result in this peak on the sky. And then a third source, which I didn't talk about yet, is PKS 1424, which is the strongest associated blazar in this 9-year ice cube neutrino sky. And then we decide, okay, let's look at it and let's study it in detail and see if it fits the picture which we have drawn from our previous analysis or not. So it is indeed high energy blazar because it also belongs to the 1%, to the top 1% in the Fermi gamma ray sky. It is detected by Cherenkov telescopes. All right, at the same time, when we looked at our data, at Mojave kinematics result, so this is the histogram in the top, in the right bottom here. I have shown this histogram already for you in this slide. I'm repeating it, and here I'm repeating it with a pane because you see that this blazar has only shown 2c as its highest VLBI speed, which is a strong indication that its Doppler factor is actually low. And it is against what I have shown to you before. So this is actually a big problem. Is it a low Doppler boosting blazar? We have a problem here. Moreover, if you look here, it is turns out to be a known problem for very high energy selected blazars, which is known as a Doppler factor crisis. Low apparent VLBI speed, high energy emission, requiring high Doppler factor. So what is going on here? We have addressed this question by stacking together 14 epochs of our observations within the Mojave program. So this is with polarization, 15 gigahertz at VLBA, and on the right-hand side, you see the outcome of this analysis. By staking this all together, and here you see the polarization image of this blazar, we have done the following. We have stacked polarization image from all these, so 42 epochs, 14 years. And here in black, you see magnetic field lines incorporated in polarization emission by just rotating the measured electric vector position angle by 90 degrees. So there is no Photoshop involved in producing this image. It is pure, we have taken the feeds, we have made this plot by rotating EVP by 90 degrees, that's it. Nothing else, didn't touch it at all. If you want to play with this, the feeds is actually made public by us, so you can analyze it yourself if you're interested, for example, to simulate it. And from that, we make the following conclusions. So first of all, just from the image itself, it kind of looks obvious that we observe the jet looking in its cone. So the jet is facing us with a very small jet viewing angle, almost zero. And then everything becomes clear. All right, if your jet weaving angle is very small, just from geometry, it minimizes the speed, VLBI speed, which we can measure from parsec scales, right? Because it moves in our direction and almost doesn't move in the plane of the sky. It also maximizes the Doppler factor, which becomes twice the Lorentz factor for a very small jet weaving angle. So as a result, it suggests a partial solution, a very obvious solution for the Doppler factor crisis. So the Doppler factor crisis can be solved if jets look directly at us. And the reason why it was not discussed seriously before is simply because no one has seen this kind of direct observational indications. And on top of that, we were very lucky that looking at us and having very small rotation measure, because almost all potentially material which can potentially rotate the EVPA was pushed away by the jet going in our direction. So very small rotation measure. We were very lucky that staking it all together allowed us to reconstruct and to get a direct detection of a strong toroidal component of magnetic field. So everything kind of fits, makes sense. Another example which I would like to discuss today before coming to my summary is a multi-messenger flare. So another specific example of a blazar. In this regard, it is blazar PKs 0446 plus 11. And for this, we have found out the following. So a high energy event arrived from this blazar a couple of years ago. And so there was an ice cube neutrino alert published in January 2024 with the energy a little bit above 100 TeV. And almost immediately we realized, and by we I mean many people in the world, because there were many astronomy telegrams published, we realized that there is a multi-band electromagnetic flare happening at almost about the same time, right? So red is the moment when neutrino has arrived. And this is gamma, X-rays, okay, whatever we have. So gamma, X-rays, optical, radio. A clear flare on the scale of about a year, which has started around the time when neutrino has arrived. And the formal chance coincidence probability here is about 2%. We do believe that in this case, we also have a small jet weaving angle. It comes from our simulations and also indirectly comes from VLBI measurements. And what we are additionally excited about, what is interesting, is that on the bottom right for you here on this plot, you can follow the changes in the direction of linear polarization in the core of this blazar. And after or around the time when neutrino was detected, the electric vector position angle, direction of linear polarization, had a swing by about 90 degrees. It stayed like that for more than a year, and then depends on how you want to interpret it, it jumped back by 90 degrees. So the 90 degrees EVPA swing is typically interpreted either as a strong change in synchrotron opacity, and once again, it has happened in the core of this blazar, so it is possible, or as a shock which either was bored or was enhanced, or its emission was enhanced, and a shock by compressing magnetic field lines, it can produce a magnetic field which would be which would change the overall magnetic field direction in the core by 90 degrees. And we do prefer a shock interpretation to the interpretation of opacity, because it's difficult for us to imagine that the core will stay opaque for such a long time. But on top of that, this is a spectral index versus time, and you see that the spectrum of the core became inverted at the moment of the flare, but then it was slowly going down, and during this time, you already would not expect the core to be dominated by synchrotron opacity. So again, we prefer the shock interpretation in this particular case, which means that a mechanism related to proton accelerations in shocks is not confirmed, but is supported by this result of the EVPA polarization swing. I come to my summary right now. So the evidence is growing for active galaxies to be efficient particle accelerators. Very high energy gamma rays, neutrino, parsec scale and variability, radio, data, observations probe the acceleration processes, the process of accelerating massive particles. And there are very exciting opportunities right now for this kind of joint studies. Moreover, I have mentioned in the very beginning of my talk that we came to Granada to learn how to do neutrino astronomy together with European neutrino collaboration. So there is an American telescope operational, there is European telescope operational and being built right now. There is a Russian telescope, so IceCube, Kempton and Baikal. Our Chinese colleagues are considering to build a huge neutrino observatory to the size of about 30 cubic kilometer, and IceCube is also considering to expand to a comparable size. So it is just a fantastic opportunity, which is echoed by the neutrino world being right now strongly, expanding and effectively supported by as infrastructures. And now moving from opportunities to physics, which I wanted to address in this talk, to our recent results, basically published last year or a few years before. We believe that we have found a partial solution to the very high energy Doppler factor crisis, and it also addresses the questions of how blazars can accelerate particles and produce neutrinos. It actually addresses the question, why would we detect active galaxies as neutrino emitters? And one of the reasons, one of the helping factors is the jet weaving angle and very high Doppler boosting. We have directly detected toroidal magnetic field component in AGN jets, and we find new indications for particle scale shocks as potentially being efficient particle accelerating sites. Thank you.
Thank you very much, Yuri, for your excellent talk. Is there any question? Yes, this one by Gwen first.
Hi, thanks for the talk. Very good. I didn't know about the last result you presented on this PKS 0446. I wanted to ask this form of chance coincidence that you're reporting over there. Is that the probability that this neutrino is atmospheric, or is this the chance coincidence that this flare is coincident with the neutrino?
Thank you very much for the question. Since I'm watching the time and I wanted to be able to give long answers to questions, is it okay if it will be not a few sentences, but like 10 sentences? Okay? Because your question allows me to discuss something which I have learned, enjoyed myself when starting to work with colleagues from neutrino world, and I realized how, what's the right word, not to be too negative, simple-minded, I wanted to use the word stupid, but I didn't, simple-minded and poor, at least my knowledge and understanding of statistics was before starting to work with the colleagues. So I will share with you what I have learned. It could be that you all know about it, but for me, this wasn't it. So, first of all, even though I have shown to you this 2%, it has little sense. And I'll explain to you what I mean by this extreme claim. So, about your question, the formal chance coincidence probability shown on this slide is 2%, is a formal chance coincidence probability of the neutrino flare or neutrino high energy event, the gamma ray flare and the radio flare to coincide. Okay? So this is the direct answer to your question. It has nothing to do to the probability, or they use the word signalness of the neutrino to be of an astrophysical origin, I can tell you what is signalness or probability for this particular neutrino to be of an astrophysical origin, and the answer is the probability is above or about 35%. It is published by S-Cube in this announcement. They might change this estimate later, but this was their fast estimate. Okay. Now, what does this mean? I already told you, this is just chance coincidence probability between neutrino and radio flare and gamma ray flare to coincide. However, the reason why it has little sense and why we should not run around saying we have such a wonderful, high probability, 2%, is because it is calculated after the fact. I have already chosen this case to be interesting. Okay? I have already chosen it. And after choosing it, I calculate the chance coincidence for neutrino and gamma ray radio. How do? I do it properly. I really calculate it properly. We have taken all Fermi data. We have taken, in this particular case, all Owens Valley data. So 15 gigahertz monitoring for like 1,000 blazars for like whatever, 15, 20 years. And we have compared arriving neutrinos, moments in time, the gamma ray light curves, really, and we have compared this case to all the other cases. And we just ask a question, how often does this happen? And the answer is 2%. But since it is after the fact, I have already chosen this as an interesting example. We should treat this with caution.
This probability, I mean, you're choosing it after the fact, but if it is a post-trial probability, then you're already taking into account that you're choosing it after the fact.
If you're saying that I have calculated correctly or we have calculated correctly, yes, we have calculated it correctly. It is a correctly calculated 2%. But it is after the fact in the sense that I am not giving here a talk, giving you a huge number of examples when something, for all the other IceCube alerts, for which we didn't have such a nice case. Okay, I'm only selected to give this talk and this story about this nice example. I didn't show you all the other not nice examples. In that regard, it is after the fact that I have already chosen it to be interesting. Okay, that is what I mean. Okay, it is not a 2% proof that blazars are neutrino emitters. That's basically what I mean. Okay.
I actually had a question which is related to that, so I'm going to jump on the topic because that has happened with other identifications actually. Whenever you have a neutrino detection from a case like this one, for example, and you associate with a multi-wavelength flare, not always the time of neutrino arrival coincides exactly, in particular, for example, with the gamma ray peak, which is the case here. And that is related also with the computation of the probability of chance coincidence, how big you consider your window for the gamma ray flare, for example. So is there an explanation in this case for this case, for example, why you didn't detect the very high energy neutrino right on the peak in the gamma rays, which is almost 1 order of magnitude higher in Planck?
Yes, but before answering this question, I'll just tell you that when we have calculated these 2%, we have made decisions, formal decisions of how do we cross-associate flares. And we just said, all right, a gamma ray flare is the following, a radio flare is the following, a neutrino event is the following, whatever IceCube has published. And then we just looked at all the data and we have said that this kind of coincidence by chance happens in 2% cases, right? So it's talking about, so it's not like we have looked at it, oh, we like this case. No, we had a set of numerical criteria, which is discussed in our paper, which we have applied to all the cases, and that's how we calculate 2%. But now coming to your question. You might all know the name, or many of you might know the name of the wonderful colleague who is one of the pioneers of high energy astronomy. His name is Felix Agaranyan.
We know him as Aharon. But yeah, we know.
He's actually yes, but he is Armenian, right? So it's Agaranyan. Yeah. The same is actually with my last name, but it doesn't matter. So he said to me once, after I had given a colloquium in his institute in Heidelberg, and I couldn't understand him, so we had to have a dinner together so that he could explain me this. He said, I don't like neutrino detectors because they are slow. And I said, what? What does it mean slow? I mean, these are like microseconds and they detect all the tracks. And so only after a couple of beers and discussions, I understood what he means. He means that if you have a neutrino flare, you have to wait long to detect it because the probability for neutrino to interact with matter is so low that you have to wait long to get at least one neutrino out of a flare. Okay? And this is, I don't like to work with them, they are slow, inconvenient. And that is exactly why the moment of time when neutrino arrives doesn't give you an exact understanding on at all on the length of the flare. Okay? Unfortunately. So the length of the flare can be as long as the whole, for example, gamma ray flare, right? It could have been detected at any moment of a long flare. And in that regard, if a flare was only 1 week long or 1 day long, then we can discuss the moment of time and we can discuss why it didn't coincide with, for example, this peak, right? But unfortunately, we don't know. And if we assume that the neutrino flare was short, let's say 1 week, the neutrino flux becomes too high. And at least we failed to SED model it. We failed to produce a reasonable SED model for single zone, okay, simple-minded SED model to be able to explain such a high level of neutrino flux. The shorter the flare, the higher the flux from this one detected neutrino. So I don't know if it is just a chance probability to detect this particular high energy neutrino within a flare which has lasted for many months. Okay? If we know this delay properly, of course, then we can use geometry, cross correlation between the light curves in order to constrain the region from where neutrino arrive. That is for sure. But to be on the safe side, we cannot say right now. Okay.
Well, yeah, thank you.
Also, I think people are starting to leave the graveyard.
Okay.
I don't think they could hear me. Can you, Yuri, maybe tell the person on Zoom they can speak?
Okay. So I'm told that if you are in Zoom and you have a question, please speak up.
Oh. Hi, Yuri. Can you hear me?
I can hear you perfectly.
Yeah, okay, hi. So I have another question concerning this formal chance coincident probability. I was asking myself the question, so you said that this is the probability of having the neutrino in coincidence with the gamma ray flare and the radio flare, for example. But in that calculation, is it taken into account that you are expecting a correlation, for example, in between the wavelengths, for example, gamma rays are correlated typically with radio. Is that taken into account or does it even matter?
It is taken into account indirectly by using real Fermi light curves and real radio light curves for about 1,000 AGN, at least several hundred AGN, in order to calculate this chance coincidence probability.
Okay, thanks.
We didn't assume anything. Whatever the data have given to us went into this calculation.
Question by Jens?
Yes. I think a similar question along the same line, because you said that it's not very clear when a neutrino would be emitted or detected actually from the long flare. Do you have comments on this regard? What would be a strategy to follow for the reaction time after neutrino events have been announced for shorter or longer monitoring problems?
So first of all, how do you address this problem? For a given source, I have discussed it. You just ask yourself a question: Can a flare be very short? And then you can properly deal with that. And at least our answer was no. So at least we can not explain it physically. So observationally, you address it by having a high number statistics. Because if you have a sample, Of course, probability-wise, your neutrinos will arrive around the moment, of the peak of this neutrino flare. So probability-wise, you will be able to do it. Now, talking about observational scenarios, I'm a very strong believer in continuous monitoring of complete samples. It's not only, and for me, it's not even most important that you don't miss an event, right? So you already observe a source when it arrives. For me, the most important is you have the statistical power to answer the question about statistical significance. And even though, statistics, as soon as you hear the word statistics, it starts to sound boring to you. However, if you talk to the people doing particle astrophysics, for them, the whole science is statistics. So your results will be completely not interesting for them, and I second it if you cannot assign a significance of your conclusions. So in that regard, complete samples are important because you understand properties of the sample. If you don't understand properties of the sample, then you can be driven by any kind of biases, and then you must understand them, or you will get artificial results.
In that sense, there is a poor value in triggered observations compared to poor monitoring.
They address different, they address different goals, basically. The goal, for example, of doing single source studies, an example here on the screen would be to answer the question, all right, neutrino has arrived, I have my multiband data, can I simulate it? So what my model physically will bring me, and in this paper we have detailed parameters of, at least for the single zone, recovered for this source. But we are completely not capable of answering questions like, does it bring us anything related to what is the number of fraction of neutrinos produced by AGN in the sky, which many people are interested right now. What is the probability for AGN to produce neutrinos in general? We cannot help here. Yes, but it's just different goals. You address different goals.
Okay, one last short question.
So you mentioned modeling, and I was wondering, in the modeling that was done, was there a good compatibility between the ice cube Moscow energy and predictions from the Milky Way and SQ?
Sometimes it is better, sometimes it is worse. I'm not sure if I have heard the full question correctly, so let us talk later. But I will give one example, if I may. There was a very high energy event produced by KM3net. Sorry, detected, not produced. detected by KM3net and published 1 year ago in Nature. And it doesn't fit very well statistical results from IceCube and other observatories. So basically, the claim there is that this is if it comes from the tail of the distribution of neutrinos as they are being detected by IceCube, this is an event as rare as 1 in 70 years. So to comply between the KM3net very high energy event and what IceCube has produced over the last 15 years. And the problem is that KM3net was only observing for 1 year. They were observing for 1 year and they have detected an extreme event, which to comply to IceCube results should be a very rare thing. And in that regard, things are not very consistent between each other. But if your question was about something more specific, then please ask it again.
How is the data there? You have the Milky Way data.
Yes.
You can do modeling on it, and from that predict the neutrino flares. And I was wondering if the energy of the observed neutrino was compatible with the data.
Yes, it was compatible, again, if you assume that the flare is a long flare.
But compatible with this neutrino and non-detection of other energies.
Yes.
Is there any other last question, perhaps? Since perhaps I'm going to ask you a short one. You were talking about KM3net, and you mentioned that you are here with your group to attend a workshop bootcamp of KM3net. I wanted to ask you, what is your prospect for KM3net in the field of blazars, at least the one you are talking about? Do you expect an improvement regarding IceCube? KM3net is now being built, and in principle it's going to be a quite sensitive instrument as well. What do you expect?
we finally have more than one guy on the street, more than one strong guy on the street. And when you have one strong guy on the street, you are in trouble, you know it very well. Because then this monopoly, it doesn't help science really well, when there's no strong competition. In that regard, I do expect things move much better just because we have more than one sensitive instrument, not right now, but soon. These are general words, right? More specifically, if I compare IceCube with KM3net, KM3net uses Mediterranean Sea, so it uses water. And it is known that for water detectors, the angular resolution, so accuracy of locating neutrinos on the sky, is higher. Why? Because transparency of water is much higher than transparency of ice. So you basically can track trajectories of muons much more accurately. And this improves your angular resolution by at least a coefficient of 2. And so after KM3net is fully built, and we are talking about the year 2030, so in about 5 years from today, it is operational already now, but after it is fully built and all the systematics is taken care of, I hope and expect for even higher angular resolution. And this is right now the limiting factor of associating neutrino with space objects. And this is truly exciting because, as I said in the beginning, they talked about HGN, but if current estimates are correct, it's only 10% of neutrinos. It's a lot of fun. And KM3net as a water detector will help very much.
So, yeah, thank you, Yuri, again for your nice talk. Thanks a lot.
So I'm right now stopping as Zoom.